second speaker is Professor Misao Sasaki. That's one comes. Thank you, sir.
Okay. In fact, I usually
No, I think
probably my neck voice. Okay. Anyway, so which one is the on? That's all.
it's good for recording.
All right. Okay. All right, so first of all, yes, happy 20th anniversary, and everything is going on well, and I hope the next 20 years will be another bright, interesting sort of, activities. Is there any pointer? Is this one? Yes. Okay. So today let me talk about this sort of three topics, which are sort of started to merge in myself, and I hope I can convince you that they are really becoming interesting. And of course, the key is this gravitational wave astronomy and astrophysics, whatever. Okay, first let me talk about the inflation. As probably all of you know, I probably don't really have to go into details. The inflation is a quasi-exponential expansion of the universe at very early stage. And originally it was meant to solve the initial conditions such as singularity horizon, flatness problem, and so on and so forth in big one cosmology, where those are assumed to be some basic assumptions. But now we know that if any of them can be said to be solved, depends on you. I mean, there's no precise definition of solving initial condition in that sense. But the most important thing is that which is not, well, for some people this was the original things from inflation, but it was not quite anticipated in the community, was this quantum vacuum fluctuations. And essentially those vacuum fluctuations during inflation becomes macroscopic due to this exponential expansion, and they give all the origin, explain all the origin of the structures in the universe, life, us, everything. Yes, all these things comes from inflation. Okay, that's the most important prediction of inflation. But of course, we do have a quite good evidence. I will just mention later. But one more thing is missing, because all these quantum vacuum fluctuations also should include vacuum fluctuation of space-time or intrinsic graviton fluctuations, and which is yet to be found, and which is related to this gravitational wave astronomy. Now, okay, so let me again briefly talk about how inflation turned into our universe. Again, I probably don't need to explain anything. But, so usually the inflation ends by after it sort of starts to oscillate around some minimum, and because inflation cannot solve the so-called cosmological constant problem, we simply assume that minimum has a vacuum energy zero. Okay. Anyway, and we call this the conversion of vacuum energy to heat. I mean, the thermal energy as reheating. I don't know why it is called re, because it has never been heated before. I mean, this is the But this is similar to this. This is in cosmology. We also call the time when the thermal equilibrium stops and the photons start to free stream. We call recombination. Okay. Actually, it's not recombination. It's the first combination in the event, but so it's similar in some parts. Anyway, and then this eventually, so inflation does give a very good initial condition for Big Bang universe, together with the very interesting quantum vacuum fluctuations, which explains almost everything in the world. The length scale of the inflation universe is approximately like this. So you have, if you take the log of length scale on the vertical axis and the horizontal axis, take the log of A or number of e-folds, then the universe is expanding proportional to the scale factor. So these red lines are the so-called constant co-moving scales, or constant co-moving lengths, or constant co-moving wave numbers. And the blue line represents the Hubble horizon scale inverse of Hubble expansion rate, and which is essentially the local causality limit. So anything occurring within that causal horizon can interact with each other, and anything which is has separated bigger than this causal Hubble horizon, you have no causal contact anything during that kind of this also has the time scale, so it's this expansion time scale. During the one expansion time scale, you cannot interact. Virtually, you don't interact at all. So as you know that all these commuting scales go out of the horizon, Hubble horizon during inflation, and comes inside the horizon after the universe comes into the universe. Anyway, the size of interest is the biggest one is 10 to 28 centimeter, which is the current Hubble horizon scale, down to possibly to 10 to 2 centimeters if the energy scale of inflation is high enough, which is the horizon scale of inflation at the end of the inflation. And well, if the energy scale is lower, then maybe 10 to 7, 10 to 6, 10 to 7. Anyway, if energy scale is lower, then we actually have some better possibility to see them from some gravitational wave experiments. But currently, the highest frequency you can achieve in gravitational wave astronomy is like 10 to 8 centimeter. I mean, frequency is like 100 plus. So this is kind of the range we can investigate by using, I mean, not maybe currently, but future gravitational detectors. So this 46 number of e-folds is the number of e-folds, the scales which you can study by gravitational waves. Now, let me just simply talk about the quantum vacuum fluctuations during inflation. It was computed by Muhanov and Chibisov even before people talk about inflation. But anyway, so essentially it's due to this some scalar field which drives the inflation, and if you consider the fluctuation of those, then essentially the mass of those scalar field must be small enough so that the leading order approximation you can ignore the mass, so it's essentially the massless field. Then you have this 3H comes from the expansion of the universe, essentially what we call the friction, yes, due to the expansion of the universe. Well, essentially the energy density dilutes when the universe expands. So this is, and the 3 comes from the 3 dimensions of space. And omega squared is just k squared over a squared. If a universe expands, the physical momentum scale like 1 over a, so it just decreases. Then what happens is that as the universe expands, then you have a almost constant h, so some constant friction oscillators with decaying or decreasing frequency. So it's, if you have some oscillations in the beginning, then this slope becomes shallower and shallower, and then you have less and less driving force to oscillate. And in the end, this completely becomes negligible, and then it stops at somewhere. And this is what happens, and you can easily compute if you assume this the quantum vacuum fluctuations, we know the initial amplitude fluctuations, and it's very easy to compute, and it can just be over the Hubble Planck. Anyway, and this equation essentially is exactly the same as the equation for the tensor modes. And so if you see some fluctuations, and we believe we have already seen them, fluctuations in those scalar modes, then we should be able to see those fluctuations in tensor mode too. Now, by the way, oh yeah, so in the case of tensor modes, of course, it's just a gravitational wave fluctuation, so you can actually directly detect if you have sufficiently sensitive detector. But in the case of scalar fluctuations, of course, since those scalar fields do not exist anymore, so if we are asked to measure those fluctuations in scalar field, we have no means. Fortunately, because it couples to gravity, or maybe you should call it longitudinal part of gravity or Newtonian gravity, whatever you call, this fluctuations, the scalar field turns into so-called curvature perturbations, or maybe gravitational potential perturbation. And the mechanism is very simple, that originally you have some fluctuations rising from essentially like in the standard quantum field theory. So you can assume that you're taking a gauge in which the spatial section of curvature is 0. So this is called flat slicing. But when inflation ends, of course, all these physics are determined by the value of the scalar field. The curvature at that time is essentially totally negligible, like 10 to minus 100 or something. And so you can completely ignore them, and everything is solely determined the value of scalar field or temperature at that time. So in some sense, this transition from inflation to the hot peak band occurs on the slice where the scalar field fluctuation is 0. So you do this gauge transformation. Then, of course, if you put this delta phi equals 0, you induce curvature fluctuations. And this is the fluctuation you measure now by SIMP and all these things. Okay, and of course, these fluctuations are seen because now this affects SIMP. How? This is essentially this so-called gravitational redshift. So this, as I said, this curvature perturbation essentially is a Newtonian potential fluctuation. And if you have some Newtonian fluctuation potential, some ground, and then if the photon is emitted from here, and if you observe it here, then the photon has to climb up this gravitational potential and the redshift. So this is the standard sort of gravitational redshift. And in an expanding universe, actually, this is modified by factor 1/3 due to the actually other sort of a little bit relativistic effect, which is not so easy to explain. But anyway, essentially, this is a gravitational redshift. So, which is called Sachs-Wolf effect, which was found in 1960s already. And also, of course, there is a standard sort of Doppler effect. So this is what you see. And you see essentially this Sachs-Wolf effect plus Doppler plus some minor corrections. And this can reproduce with your eyes essentially the same picture as it is here. But anyway, this is the real one from Planck data. And fluctuations of order of 10 to minus 5, which is perfectly fine, and it's perfectly consistent with all the structure formation scenarios. Of course, we don't know how our life appeared, but at least we know sort of how the galaxy sort of developed from those fluctuations and so on. Now, of course, as I said, another most important part, which has not been observed yet, is so-called cosmological gravitational waves. And the scalar field produces essentially the curvature perturbation, which produce density fluctuations. And these are sort of scalar modes. So from the polarization-wise, it produces only E mode polarizations. While the tensor fluctuations can produce so-called B mode fluctuations. B mode is parity odd modes of fluctuations. Or maybe in the pattern it's something like this. And we know that these cannot be produced by scalar perturbations. This is a linear order. So, so if you measure the speed mode carefully enough, then you will be able to see the primordial gravitational waves. So this is actually the largest interferometer in the world. You use the whole universe as the interferometer to measure the gravitational waves. Now, we know that the Planck made a very strong constraint on the inflation models. The so-called scale spectral index is slightly less than 1, and s equal 1 corresponds to scale invariant spectrum. So this is slightly red, but this seems to be perfectly consistent with this, some of the typical models of inflation. While the so-called tensor to scale ratio, the amplitude of this gravitational wave fluctuation seems to be small. The ratio is less than 0.1, which is not so usual because as you could see, this is the famous diagram of the tensor to scale ratio on the vertical axis and the horizontal axis is particle tilt. And if you consider various types of inflation models, many inflation models are already excluded from this diagram. And for example, this simplest, say, quadratic potential model, so-called chaotic inflation model, is excluded by almost 3 sigma. I mean, if you just take blue speed and 2 sigma, it's still almost excluded. So this means that there's some element of non-canonicality seems to be needed. And I hope this non-canonicality is related to something gravity part. Essentially, the inflation actually is dominated by scale field, and the scale field determines metric and everything. So in some sense, you can call inflation as a scale tensor theory, or you can regard this as some kind of platform of modified gravity theories, and some of those important sort of consequences, this may depend on these modifications or maybe additions of new terms during inflation, which modifies gravity or maybe geometry. Now, this is the gravitational wave from standard inflation predicted. And this is the line, and this is the strain sensitivity and frequency, and from 10 to minus 10 hertz to about 10 to 5 hertz. And the prediction is here, and all these lines, this is the LISA expected sensitivity, this is the square kilometer array, and so on. This is LCZT, that corresponds to Kagra. But anyway, advanced LIGO, etc., etc. They seems to be all above the predicted line. So at least this is another sort of motivation to think some modification of gravity. You need some hopes to develop some new detectors and some new experiments, right? And if you just stick to the standard model of inflation, then it may not be so encouraging. While, of course, I mean, just making it encouraging maybe is not so good, but still, having some more interesting ideas and which maybe actually measure within a few years or maybe. Kaisa-san yesterday said it may take about 50 years or so, but I cannot wait 50 years because by then I will be dead. So at least within my lifetime, I'd like to see some of those signals. Okay. So one idea is this. This is our recent idea that if you make actually this tensor mode massive, this is possible during the inflation. By the way, this is different from so-called standard massive gravity. Graviton becomes massive because graviton has 5 degrees of freedom, and which is due to this quantum invariance and everything. But in cosmology, we don't need the invariance. forget about quantum, then invariance. Then you can just focus on the tensor modes. And you can make tensor modes simply massive during diffusion. But of course, they cannot be massive now, so the mass becomes zero. This means that this mass of tensor modes should depend on, let's say, some value of infraton or maybe time derivative infraton, whatever. So in this way, you can make the tensor modes to be completely massless today, but very massive during inflation. This can make the spectrum blue. And if you make this spectrum blue enough, actually you can already how to say, exclude such possibilities. For example, if I make this m square over h square is 0.6 during inflation, this is already crossing a advanced LIGO is here, and so the current LIGO is perhaps crossing this line already. So you can already exclude such model. And also you have this square kilometer array thing, which can actually go down very deep. If we have this LIGO or maybe something similar, DBO or whatever, then you can really, I mean, as we have seen that this can actually barely reach the level of standard model of inflation. But as soon as you have some blue spectrum, this can be definitely observed. And this is a very, very interesting predictions. Anyway, now let me turn to gravitational wave physics, astronomy. As we have all heard, the LIGO detected this the binary black holes, and so the dawn has arrived. But they are quite unusual. They're huge, which has not been measured by those X-ray measurements and all these ordinary black hole binaries and so on and so forth, or transients and so on. Anyway, so usually they are less than 10 solar mass, while most of the LIGO events, well, they're only 3 or 4, 3.5. So still, statistically, there's nothing to say. But at least there are indications that LIGO seems to see something much bigger than usual. And they apparently are isolated, so we cannot see them. Now, and also another important thing is this. The spins, intrinsic spin of the black hole, if they are formed from some standard gravitational collapse, you would accept this spin to be very high, highly rotated. For example, if the sun becomes a black hole, as it is, then actually the spin of the sun, now it looks like very, very slow rotating, but it is greater than the maximum power. So you have to get rid of some angular momentum to form black hole. Okay? So this means that all these astrophysically made black holes should have very large spin. That's the expectation. While LIGO data shows that it's not so. It's their black holes much less spin, and this is strange. But sorry, why I have this? Sorry, maybe I got mixed with. Anyway, so future, this is we have seen this yesterday, so forget about this. And Kabra, we have seen this again. Oh, by the way, so the one thing, just stepping aside of my topic. So Kabra's here in NCTS just on exactly right in the direction of southwest, with exactly about 2,000 kilometers. I think this is a good location for another interference, I mean Kabra, yes, okay? So I hope you talk a little bit more about the future of Kabra, please. Anyway, and we have all this future space-based project. I don't know why they're here, but we can see. Wait a minute. Oh yeah, the whole point was this LIGO spin, all these things can be explained by primordial black holes. Okay. So now comes primordial black holes. So primordial black holes, what are they? They are the black holes formed before recombination epoch, or before, let's say, during radiation dominated time. So and at that time, of course, you cannot collapse anything except if you have sufficiently large fluctuation on Hubble horizon scale. And so on the Hubble horizon scale, you have some essentially, if you talk in terms of density perturbations, you must have a density perturbation of the unity, and which can collapse to form a black hole. And such a large perturbation may be produced by inflation. There are so many models. Well, this is actually the scenario. I could go back as much as possible, but maybe there are someone before who talked about this origin of primordial black holes from inflation models. I have written some of it somewhere here. Anyway, so this is a natural thing, and especially if you remember this figure. Yeah. Yes. Now, observationally, what we are measuring is from all the cosmological observation only in this 1 or 2 order of magnitude below, say, Hubble scale. This is just 1 or 2, and which corresponds to this area. But primordial black holes, as I said, it's somewhere around here, so it's way below the sort of large scales, and which are completely out of cosmological observational range. So you need some other means to detect things. And also, during inflation, you may have some phase transition and so on and so forth, which can create a huge amplitude of fluctuations. Of course, if it is too large, they are already excluded because we don't see. I mean, our universe would be completely dominated by primordial black holes, and but we don't see. So this means that actually we may have some primordial black holes in the universe. They may be a dominant component of the dark matter, which may not be quite plausible, but anyway. And some of those so-called supermassive black holes, we don't know how you can form this from simple astrophysical constellations. So they may also be primordial. But anyway, so it's always interesting to think about this possibility. Of course, astrophysicists never like them. Yeah, we anyway. So how they are made? This is a simple introduction. I mean, as I said, this is the curvature perturbation which produces density perturbations, and if the density perturbation is related to the curvature relation with this in the Fourier space, like with this factor, where this k square over a square is just a wave number, and if a wave number is equal to Hubble, or the wavelength is equal to the Hubble scale, horizon scale, the delta over rho is essentially equal to the amplitude of curvature perturbation. So if this is over the 1, or actually order 1 is too large, usually over the 0.1 or something, then there's a chance that this can cross the black hole. And the size of the mass of black hole is given by this formula, and if you want to have black hole to be about 20 solar mass, the scale is about 1 megaparsec, not 1 parsec, which is 10 to 18 centimeters. And also, because of this, because of horizon scale, where the universe cannot be rotating, it collapses by itself, the spins of primordial black hole are supposed to be constantly very, very small, which is perfectly consistent with light. And there are some constraints on the primordial black holes. Some people say that it cannot dominate the primordial dark matter. Maybe yes, maybe not. But the whole point is that at least, but it may contribute about 10% of dark matter, which is appreciable. And actually, we have a scenario, models which explain this LIGO black hole mergers by primordial black holes. But in this case, if you actually consider the free body interaction of those primordially generated black holes, then you find that the binary formation rate is much higher than expected. And this actually means that if you don't think about the rate we have seen, then the amount of those black holes it would be about maybe 1% or 1/10% of dark matter. So it's completely within the range of the allowable range. Anyway, and this can be tested by gravitational wave detectors, the scenario, because by definition, primary black hole exists from early time in the universe. So if you go back deep in the redshift, you will see that never decreased. Okay. So this is the clear signature from using all these future advanced detectors. And we can clearly, if we see this tendency, we win. So I'd like to see it before I die. Anyway, so this is the summary, and you said, as I said, the primary black hole formation, if like black holes are primordial, then this sort of proves the physics on the scale of 10 to 18 centimeters. And as I said, furthermore, if there are some modified gravity or massive tensor moles effects, then these may be even tested at this sort of LIGO, Virgo, Kagra, or maybe Misao, maybe Taiji, all these things. So now, and of course, I didn't really talk about this, but as I said, that the CMB can sense gravitational waves from inflation on this horizon scale almost. So at least you have three interesting range of frequencies where you can look for signs of inflation and its physics. And this can be only done by gravitational wave astronomy. So to summarize, inflation has become the standard model of the universe, of course, but further tests are needed to confirm inflation. And one of the most important ingredients would be the cosmological gravitational waves, and they are the key to the understanding of inflation. And the LIGO detection gravitational wave are first milestone, and the gravitational wave physics of astronomy, and now we are in this era of gravitational wave astronomy, and this may be the key to understanding inflation, as I said. And one of interesting scenarios which should be tested hopefully is that the LIGO may be primordial. And currently, multi-frequency gravitational wave astronomy as a physics arriving soon, and some more exciting things will be seen. And gravity will be an essential tool for exploring physics of the unknown universe. Thank you very much.
Questions?
Well, so what kind of mechanism do you have in mind to enhance the fluctuation?
Oh, yeah. Yes, actually, as I said, since the mass of graviton, so this tensor moles, mass depends on scarcity, so or influence. So let's say it depends on pi squared. Then during this damped oscillation period, mass oscillates. Yes, mass square oscillate. This is the Matthew equation. It's used in so-called preheating scenario, but in this case, actually, it's much stronger than preheating. It can just enhance all the spectrums outside the horizon to whatever you want. I mean, actually, so you do have a very strong power on this. Yes.
And to produce the primordial black hole with, well, so 30 solar mass, the frequency must be, well, so the wavelength must be very short.
Yes, yes.
So
but which is I mean, this is the scale we want to test this massive gravity theory. But this LIGO primordial black hole is, in that sense, somewhat, I mean, larger scale. It's a 1% scale.
Right.
want to ask the question about the massive tensor mode also. The standard way to make massive gravity has a problem with cosmology. So
Yes.
would that be also
No.
something?
The whole point all this theory has is that they have to assume quantum invariance. But we don't. I mean, you don't need, the quantum invariance means the graviton must have high degrees of freedom. And this is already the problem because as you everyone knows, perhaps the gamma ij, the metric tensor, spatial tensor has 6 degrees of freedom. You have to get it in 1. This is the famous tensor ghost, or it's the conformal mode, same. And usually this is killed by Hamiltonian constraint, but in the absence of Hamiltonian constraint, you cannot kill, and that's a real problem. And if you want to try to kill something, then something arises. But at least in the flat background, you can consistently formulate. This is the famous so-called Gram, Canada's BRG model. But as soon as you apply it to cosmology, then you have a problem again, because essentially you assume some total invariance, which is inconsistent with the symmetry of the universe, or non-symmetry of the universe. So forget about symmetry. Forget about quantum symmetry. You just focus on some covariance, but you break local roles. And this is true in cosmology anyway. You have CMB frame, frame in the universe. This is what you need. And actually, you can consider this as a spontaneous breakdown in terms of Higgs. So you introduce 4 scalar fields. One scalar field breaks the time translation, and this will be the inflaton. Okay, so inflaton specify some slice. Now, 3 other holes, which specify some particular spatial plane, which breaks essentially, in some sense, this 3 quotations covariance to make tensor modes massive. So this is our model, and which is perfectly consistent.
Does it have the mass has an effect on the black hole?
Sorry?
The mass you introduced, does it have an effect on the primordial black hole or whatever black hole?
Oh, well, no. So about primordial black hole case, when we still this massive gravity case and the primordial black holes are not related yet. Yes. That's one hope, of course. And then everything, because if you can explain everything with one model, that will be fantastic. But for the moment, I don't have it yet.
Okay, let's thank Professor Sasaki.
Thank you.